My name is Nadine and I'm happy to present our work, Unsupervised Video Representation Learning by Bidirectional Feature Prediction. In unsupervised representation learning, the goal is to learn high-level abstractions from videos without using human annotated labels. Instead, we rely on so-called pretext tasks, which can be defined based on the unlabeled data alone. The temporal structure of videos naturally provide numerous opportunities to construct such pretext tasks. For example, a popular approach is to predict the future of some form. While future prediction has been extensively explored, the unobserved past is widely overlooked. We argue that the supervisory signal that originates from unseen past frames is complementary to that of future frames and propose to exploit both signals. A straightforward approach for prediction is frame reconstruction. However, this requires to model a data distribution which may not be necessary for representation learning. Instead, we predict the features. Still, the past and future distribution is inherently multimodal, and we can address this by using a contrastive loss. In contrastive learning, the goal is not to accurately predict the feature, but rather to pick the correct positive pair from a set of negatives. The set of negatives is vital for this loss, and while random videos form the basis, more challenging negatives are required. For example, the DPC method considers spatial negatives here by treating different spatial locations of the feature map as negatives. We investigate different approaches to incorporate both past and future prediction and visualize the effect these have on the feature space in the gray sphere of the figure. Here, proximity indicates the similarity of features. We argue that an ideal feature space has two properties. First, present, past, and future are similar, and second, past and future are distinguishable given present. The first approach is disjoint prediction. Here we predict past and future independently. This approach only satisfies the first property, as the model is not required to distinguish between past and future. The second approach distinguishes between future and past by including the past features in the set of negatives. However, this only satisfies the second property, as now the past feature is dissimilar from the present and future feature. This may encourage the model to remove high-level abstractions that are shared across the video, for example, the action class, and consequently it may lead to a degenerate solution. Only with joint prediction we can satisfy both properties. Here we construct joint features of past and future and obtain a difficult negative by swapping the order of future and past. Now the task is to predict the joint past and future feature such that present, past, and future are similar, while distinguishing between the wrong order of future and past as well as random videos. We validate our design choices empirically. Here we can see that disjoint prediction does not improve over the individual prediction of future and past. The second approach that uses past as negatives leads to a drop in performance, validating our argument that this is a degenerate solution. Only our approach with joint prediction improves over the individual prediction of future and past and achieves the highest accuracy. We make an interesting observation regarding the use of spatial negatives versus independent spatial augmentations. Spatial negatives, such as those used in DPC, learn features that are variant to the spatial location, encouraging local descriptors. Instead, we propose to apply spatial augmentations to past, present, and future independently. This aims to learn features that are invariant to the spatial location and encourages global descriptors. In Table 2, we show that spatial negatives are useful in early layers where the receptive field is limited. In later layers where the receptive field grows, a global feature is favorable, and our method that uses independent spatial augmentations instead of spatial negatives is superior. Finally, we compare our method to other unsupervised methods for video representation learning. We follow the common protocol where we pre-train on the large-scale kinetics dataset and fine-tune on UCF and HMDB. We outperform future prediction on both datasets and surpass many previous methods on HMDB. Note that ResNet 34 and S3D are deeper and computationally more expensive than our ResNet 18. Thank you for your attention.